This is worksheet 4 of the thermochemistry packet. I'm actually on the second page of worksheet 4. It would be worth taking a look at the first page because it describes each of the steps that I will go through, and you can always refer back to it when you're working on these problems individually. But the basic idea of Hess's law I have written up here, and you should write it down also, which is that anything you do to an equation, you must also do to the enthalpy, which you'll remember is symbolized with the triangle H. So the reason that we use Hess's law is sometimes we as scientists want to study an equation that is too costly or too difficult to perform in a laboratory. And if we can come up with 2 or 3 or 4 smaller and less costly equations that we can combine together to create the larger equation, then we can study each of the smaller equations and combine the results together to assume what the results of the larger equation would have been. A real-life example of this is studying acid rain formation. To try to perform a full acid rain reaction in a laboratory is impossible for various practical reasons. So if we wanted to know the amount of heat released in acid rain, we could break that into 2 smaller equations and then add the enthalpy of each of the smaller equations together. And if you want to know more about that, then you should read the first page of this worksheet. But if you don't want to know more about that, then we're just going to go through some example problems here. So we'll go through 2, and then you'll do the rest on your own. I do want to warn you that this is something you're going to have to focus on a little bit. These problems are a little bit like puzzles, kind of like balancing equations are a little bit like puzzles, and it's something that does take some practice. And because of that, it might be worth doing some of these in pencil as you get used to things. So if you are approaching a Hess's law problem, you want to take a look at what the desired equation you want to end up with is. So this would be the big equation that maybe you can't perform in a laboratory. And in order to get to that big desired equation, you're going to be given 2 equations for our purposes. In more advanced classes, it could be 3 or 4 or 5 equations. So here are your 2 sort of smaller equations. And your goal is to somehow combine the 2 smaller equations so that when you add them together, you get the larger equation. And if you do that, then you can combine their enthalpies, their delta H's, together to get the delta H of the larger equation. And that's really our goal, is what is the change in enthalpy of this larger equation. So when I take a look at this first problem, I see that on the left side of my desired equation, I have Sn and 2 Cl2s, 2 chlorines. And when I look at my given equations that I'm going to add together, I see that I have Sn over on the left-hand side, and I also have, between the 2 of them, 2 Cl2s over on the left-hand side. Okay, so I have the amount of Sn and Cl2 that I need. And they're also on the correct side of the equation, the side, the left, in this case, the left side of the equation. And then when I look over at the right side of my equation, I see that I want to end up with SnCl4 over on the right side. And if I look at my desired equations, I see that, sure enough, I've got, if I look at my building equations, I see that I have SnCl4 over on the right-hand side. Which means that somehow I'm going to have to get rid of the SnCl2 on the left in the second equation and the SnCl2 on the right of the first equation. And I want you to watch how this is going to happen. I'm going to rewrite the equations down here. So I have SnCl2 forming SnCl2. I'm going to rewrite the enthalpy because that's going to be an important part here. And the sign is important. Remember, if it's a negative sign, that means we've got an exothermic reaction. And I'm going to rewrite the second equation. SnCl2, Cl2, forming SnCl4. And I will rewrite the enthalpy, which is negative 186 kilojoules, also an exothermic reaction. And then what I'm going to do is I am going to add these 2 equations together. And when I add them together, over on the left-hand side, I have the Sn from the first equation. I have the SnCl2 from the second equation, and then I also have two Cl2s from the first and the second equation combined. So I'm going to total those up there. On the right-hand side of the equation, I have SnCl2 and SnCl4. Right? To get the enthalpy here, then I'm going to have to add a negative 325 and a negative 186, and I believe that gives me negative 511 kilojoules. All right. Now, the next step that's important is to look and see if you have anything that is the same on the left and the right-hand side of the equation, because if you do, they're going to cancel each other out, much like in an algebra problem. So what I notice is that I actually have SnCl2 on both sides of the equation. There aren't any other things that are the same across both sides of the equation. And so what I'm going to do effectively, as though this were algebra, is I'm going to subtract SnCl2 from both sides, getting rid of it. They cancel each other out because they're the same on both sides, which means that all I'm left with is the Sn and the 2Cl2 over on the left side, and over on the right side, the SnCl4. Okay? And because I already had added together over here my enthalpies in the past, that's going to just continue to be 511 kilojoules. I'd already added those. All right, and so my answer actually in this case is the negative 511 kilojoules, but it's really important to make sure that this equation here is the same as the desired equation that I was trying to get to up at the top. And so if you compare those two equations, you do see that they are indeed the same. Now, this was a relatively simple one. It may not seem that way, I recognize, but it was actually a relatively simple problem, and so I want to go through one more just to make sure you have some good examples to guide you through what you'll do independently. So, we will do one more here. In this case, my desired reaction is up here. And, of course, the goal is always to figure out what would be the enthalpy, the delta H, for this large equation. And I'm given two sort of building equations I'm going to try to add together in order to get the larger equation, the desired equation up at top. And if I just take a close look at this, I will notice that in my desired equation, I want to have 4 aluminums on the left-hand side. And I'm already getting that from my first equation here. I will notice that I want to have 2 aluminum oxides on the right side, which I'm already getting from my first equation, which makes me think that that first equation is probably something I want to leave pretty much as is, which is what we did with both of the equations in the previous problem. We left them as is, and you're probably thinking, well, how would we change them? So this is what I want to show you here. If you look at the desired equation, you'll see that you want to end up with 3 MnO2s, manganese oxides, and you want them on the left side of the equation, the reactant side. In your building equations over here, you've got MnO2, only one of them, and it's on the right side of the equation. So we're going to actually have to do 2 things when we go to rewrite this equation, that second equation. We're going to have to reverse it. So we're going to switch the Mn and the O2 that are currently reactants and make them products. And we're going to take the MnO2, the manganese oxide that's currently a product, make it a reactant. And I'm going to show you how to do that. Then we're also going to multiply this equation by 3, because instead of just having 1 manganese oxide, MnO2, we want to have 3 of them. All right, so first I'll rewrite my first equation, which is pretty straightforward. I have 4 aluminums, I have 3 O2s, and they are forming 2 aluminum oxides. And the delta H, I'll just rewrite, is negative 3,352 kilojoules. the second equation now I am going to reverse, meaning what was my product, the manganese oxide, is now going to be a reactant. And what were my reactants, the manganese and the oxygen, are now going to be my products. The other thing I'm going to do is I'm going to multiply the whole reaction through by 3. Because I want to have 3 of the manganese oxides over on the left side, so it's like the desired equation up here. And I can't just multiply the manganese oxide, I have to multiply everything by 3 if I'm going to multiply one thing by 3. Now, the thing that a lot of people forget is, remember, whatever you did to the reaction, you have to do the same thing to the enthalpy, the delta H. So since I reversed the reaction, I am going to reverse the sign of the enthalpy. So instead of having a negative 521, I'm now going to have a positive 521. And since I multiplied my equation by 3, that 521 needs to get multiplied by 3, which means I am now going to have 1,563 kilojoules as my enthalpy. Very important not to forget to do that. So I now add everything together just like I did last time. So I have 4 aluminums, I have 3 O2s, I have 3 MnO2s. That's over on my reactant side. And then on my product side I have 2 aluminum oxides, I have 3 manganese, and I have 3 oxygens. And because I added these reactions together, I'm going to add my enthalpies together. So I'm adding the negative 3,352 and the positive 1,563, and I believe that gives me a delta H of 1,228 kilojoules. Now, the last thing I'm going to do here before finalizing is to compare my left side versus my right side. And when I do that, I see that on the left I have 3 oxygens, and I also do on the right, which means that I'm going to need to subtract from both sides, just like this was an algebra problem. I don't have anything else in common on the left and the right side, so I'm going to finalize here. I have 4 aluminums, 3 MnO2s, 2 aluminum oxides, and 3 manganese, and my delta H is what I already calculated it to be, 1,228 kilojoules. So you have a total of 6 problems to do, so you'll have 4 more left when you get to class. And as I said, this does take a little bit of practice, so that's what we will work on the next time we are together.